Hello and welcome. We're excited to talk with you today about what for some can be the hardest part of a project, getting started. That's right, we're talking about pilot studies. How do we unlock efficiency and find the optimal sampling sweet spot for stereology studies? Thank you for taking the time out of your day to be with us. We're really glad you could be here. We're really looking forward to this discussion on a subject we get many questions about. Now, before we get started, some introductions. I'm Nate Leese, the Stereo Investigator Product Manager. We have Dr. Dan Peruzzi. He's a senior member of our support team and research liaison. Along with Dan, we have Aidan Sullivan, our tech support manager. Okay, so one of our favorite parts of doing these webinars is interacting with everybody out there. So I wanted to quickly go over how to submit a question. I know it's Zoom and it's 2024, but just to make sure everybody has this down, just click down on the Q&A button at the bottom of the screen to open the question and answer panel, then type your question, press enter. We'll take breaks for questions, but feel free to submit those at any time. Okay, back to the webinar. In this presentation, Dan will be helping Aidan with getting started using unbiased stereology to answer her research question. Let's listen in.
Hi, everyone, and thanks for the introduction, Nate. And Dan, I'm so glad to have your help today as I start this new research project. I am trying to estimate the cell population in the right dorsal part of the anterior cingulate area in the mouse brain to determine if there's a difference in cell numbers with treatment. My problem is I have no idea what to choose for my stereology parameters.
Okay, well, welcome, and I'm glad you came to me for help. Anterior cingulate gyrus is an interesting part of the brain. I'll be asking a series of questions to help us set up this pilot study. The first thing I want to ask is, do we really need to do quantification? In other words, if you are if you have the idea that there is a higher density of cells in one group and the higher density of cells in one group than in the other group, and you can show this difference in every section that you look at, it's obvious, then you can simply show the images for the two groups, and that will show that there is more cells in one group. But if it's more subtle than that, and you can't tell by just looking, which is represented by this cartoon between group 1 and group 3, then that is the time to use unbiased stereology.
Okay. Well, I expect my treatment will reduce the cell populations in the right dorsal portion of the anterior cingulate area, but when I look at my sections, I don't visually see a difference in my populations. So I'm looking to use stereology to verify if there really is no difference or tease out a statistically significant difference if one does exist.
Okay, sounds like we do want to use unbiased stereology. So my next question is, how are we visualizing your data?
To image my sections, I have used a resonance scanning confocal microscope and acquired slide scan image stacks of the top right region in my coronally sectioned tissue with a 63 oil objective.
So just going to jump in real quick. Aidan is bringing her image data in just one of many different imaging modalities we support. You can work directly on the microscope as Stereo Investigator fully integrates with motorized microscope components. You can open and analyze bright field or fluorescent images from a wide variety of sources as well, from confocal scopes to slide scanners. Stereo Investigator can also drive and connect to structured illumination devices such as the MBF Bioscience that produces a confocal-like image and can be added onto most microscopes. Additionally, we also support the Zeiss Apotome and Olympus DSU for this style of imaging.
Wow, that sounds really flexible. I'm so glad that my image format is going to work well with Stereo Investigator. Here, let's take a look at some examples of my images. On the left side of the screen here, I have a single plane of the right mouse cortex, including the dorsal part of the anterior cingulate area with both GFP and DAPI labels shown. But I'm specifically interested in counting the blue channel. So let me play this video for you to show you that 3D section in just the one channel. And you can see as it rotates and shows you the Z projection, this is a stack made up of 46 Z planes with a total extent of around 20 microns. And if we look at the zoomed in view of this slide scan stack, you can see the cells are visible, and I do have many Z planes that actually span through these cells, which is going to allow me to identify the unique point that I plan to count, the cell tops.
Okay, that is very good staining, and we are going to be able to see those cells. So that's a big, you're kind of way ahead of the game there. So you want to estimate number, but I'd like to remind you that if other things come up in your study, we have other probes in Stereo Investigator, and we can also estimate length, surface, and volume. But let's concentrate on number for now. So at the bottom on the left chart, it shows cells in 3D on the left, and then how you would see them in the microscope on the right. And if we look at the chart on the right and go to the right side for the number column, on the top, that again is showing the cross sections of the cells for number. And then if we go down to the probe row, that shows a dissector, which is a three-dimensional virtual space that we're going to restrict ourselves to counting. We're only going to count the cells if the top of the cell is in that probe, which is shown at the bottom. And so that's what we're going to concentrate on today is number. But I also want to point out that on the left, we can see the 3D and the 2D representation of length and surface and volume. So all three of those can be estimated. And if we look on the right, on the top, we see the illustrations of the tissue that we're looking at: volume, surface, and length. Volume is probed with points, and surface is probed with lines, and length is probed with planes. And on the bottom, it shows the interaction there. So keep in mind, we can also estimate length and surface and volume, but we're going to concentrate on number today.
Okay, so what you're telling me is I can use different probes to estimate different aspects of my tissue, like volume, surface area, and length. But because for my study, I'm interested in counting the number of cells in my region, we're going to be using the volume number probe, shown over here. And we're going to be counting the cell tops that intersect with our optical dissector here.
Okay, so let's keep concentrating on the optical fractionator to estimate number of cells. And this shows the formula that's used to make the estimate. So on the right at the top, it shows the formula, and N is the estimate of the number of cells in the region that you have sectioned through. Sum of Q minus is your raw data. So that is all the cells that you've counted and all the dissectors you're using and all the sections that you're going to look at. So that's the raw data. That's all of your cell tops. Though that's only from where you've looked. And so what we want to do is take the volume fraction, which is represented by the three terms on the right, T over H, 1 over ASF, and 1 over SF, section subfraction. That makes up the volume fraction. We take the reciprocal of that and multiply it by Q minus to get an estimate of all of the cells that are there. So Q minus, if we look on the left, Q minus is the number of cells counted. HSF is the height subfraction, and it's listed as H over T. That's dissector height. If you look on the right, there's a illustration of a dissector with red sides and green sides on it. So we're talking about the height of this virtual space that we're only going to count the cells if the cells are in that dissector, divided by the thickness of your sections. But in the formula, that shows up as T over H because we take the reciprocal. For the area subfraction, we have the counting frame area, so that's shown there, and divided by the grid step area, which is shown there. And in the formula that appears as 1 over ASF, because we want to take the reciprocal in order to extrapolate. The section subtraction is probably the easiest to understand. If we are skipping every 10th section, then it's 1 over 1/10, which would be 10. You're skipping every 10th section, so you need to multiply by 10.
All right. Thanks so much, Dan. So just quickly wanted to go over, we're really interested in that height subfraction, the area subfraction, and the section subfraction. So defining and tuning those to maximize our efficiency. These stereological sampling parameters are really at the heart of the pilot study, honing these variables and determining the best way to move forward with the study. We'll be discussing each of these as we move through today's webinar. For those of you that are interested in more information about this outside of this webinar, we do have other ones on our website and YouTube channel that'll go into some greater detail.
So section subfraction, the area subfraction, and the height subfraction are very important, Nate, and they're showing up again here in this slide on step 3. This slide outlines where the pilot study fits into your whole experiment. So number 1 is the creative part. That's your ideas and your hypotheses. And kind of maybe one of the hard parts of this whole process is to go from 1 to 2, and that's to translate your ideas into what kind of data do you need. And that's what we hope you have already know and have thought about before you use Stereo Investigator. Number 3 is the pilot study, and as Nate has stressed, the whole idea of the pilot study is we're trying to figure out how many sections to skip, what percentage of the area to sample, what percentage of the height to sample. Section subfraction, area subfraction, height subfraction. Once we figure that out, number 4 would be to go ahead and use the probe on all the animals in all the groups, and then perform your deviation from the mean, classical statistics. There's a reference there that is a good guideline to help with that. And you're going to have one of 2 results. Either there's going to be a significant difference between your groups, which means you have set the pilot study up correctly, you've set up SSF, ASF, and HSF correctly to find a difference. If there's no significant difference between groups, this pilot study, the design of the pilot study is there so that you can know that you have done enough sampling to tease out a difference between groups if there was a difference there.
Alrighty, so we're just getting started and we've already covered a lot. We're going to pause here for questions, and while we give folks some time to send those in, I'll quickly summarize what we talked about so far. Why might you need or want to use stereology? Different imaging techniques that are compatible with Stereo Investigator. We touched on some different stereological probes and reasons to do a pilot study. All right, so again, we'll pause for questions.
Doesn't look like we have any questions right now. We will have more opportunity for that, so we'll go back into it.
Yeah, Dan, I really appreciate you showing me where the pilot study fits in within the entire stereology process. And after seeing that, I do think the pilot study is my next step. As you mentioned, I have my research question, and I know how I can answer it using Stereo Investigator's Optical Fractionator workflow. I've looked into the literature and stereology studies that have been done on my region and cell type in the past to get a sense of what others have used for parameters. But my study and treatment is slightly different, so I'm trying to determine how much to sample for my unique data.
Okay, yeah, that is a good idea to check the literature. I'm glad you did that. So this slide is really, as Nate was saying, the crux of what the pilot study is for. We want to figure out the section subfraction. We can see where section subfraction is in the formula. And so we want to choose an interval for a section subfraction that will give us about 10 sections. So that's the criteria for the section subfraction. End up with about 10 sections to look at. For the area subfraction, we can see where that is in the formula. We want to choose an interval that gives a mean of about 10 counting sites. And we can even be more specific than counting sites. These are going to be dissectors. where we're looking for the tops of cells, because your hypothesis has to do with a change in the number of cells. Number 3 is the dissector itself, the probe that is used to estimate number of cells. We want to size that so it gives a manageable number of events. And instead of events from now on, I'm going to be saying cell tops, because the event that we're counting for estimating number of cells is putting a marker on the top of the cell if it is in the dissector. So 0 to 5 cell tops will yield about 250 cell tops total. That's 10 sections times 10 sites times 2.5 cell tops. So we're looking for a Q minus, in other words, the number of cell tops that you have marked, of about 250. This is the criteria for the pilot study.
Yeah, I think that makes sense. Let's start with looking at my data and see if we can figure out what an optimal section subfraction would be then.
Okay, to start this pilot study off, you're going to select one animal, hopefully a representative animal, from a group.
Okay, do I choose a treatment or a control animal for the pilot study?
Well, that's a good question. We actually want to do a pilot study on a representative animal from each group because the experimental protocol may have changed what parameters are called for.
That makes sense. Okay, well, let's start with my control animal for now. Throughout my entire region, the anterior cingulate area, I have about, on average, 156 sections, or specifically 156 sections in my representative control animal that I'm going to be using for the pilot study. And I've cut those at a 30 micron cut thickness at the cryostat. And I definitely don't want to use every section for my stereology study. I'd like to use those sections for complementary experiments as well.
Yeah, that would be impossible, and it's really not needed. So notice on the right, we've pulled up a Allen mouse brain atlas to show where the anterior cingulate gyrus is. On the left, we can see that Aidan has cut the anterior cingulate gyrus into 154 sections. And we also have a cartoon there that's not to scale, but that can help us illustrate what we mean by section interval. So Aidan, what are we shooting for when we talk about the section subfraction? How many sections do we want to be looking at for the pilot study?
You said for the pilot study we should be aiming to get 10 sections throughout the entire region. So if my region that I've cut has 156 sections total, then would that mean we want to use a section interval of every one section in 16 to count on?
Yes, section interval of 16. All right, we already have a parameter. We're going to use a section interval of 16, and that's in order to give us about 10 sections. But we don't want to start on the first section in the region for every animal, because then we'll be looking at the same 1/16 of each anterior cingulate gyrus. So we actually need a random start. So here are 3 possible examples of using a constant interval, 16, but doing a random start between 1 and 16. In this case, the random start was 3, and we end up with 10 sections. For another animal, the random start might be 1. And again, we end up with 10 sections. For a third animal, another random start might be 6, and we end up with 10 sections.
That makes sense. So when I did this for my control animal, I pulled in that sample in Stereo Investigator, and it randomly generated a starting section for me when I told it that I wanted to use a section interval of 1 and 16, and it selected section 15 as my starting section. And then from there, it created the serial section manager that you see on the right side of the screen. And you can see we're starting on section 15 and then going up by 16, an interval of 16 for every following section. And if you counted these, you would find that I only have 9 sections. And you can see that my last section, my 9th section, is 143. If you add 16 to that, I would be getting section 159. But remember, I only had 156 sections cut through this sample, so I don't have my 159th section here. That's not available for this sample. Is it okay to have 9 sections like this? I know we were aiming for 10 for the pilot study, Dan.
Yeah, a lot of scientists think about keeping things constant, and so they get a little bit worried that we're not using 10 sections for every animal, but we are keeping something constant. What we're keeping constant is the interval. Every 16th section is what we're using. That needs to be constant for the formula when we extrapolate the section subfraction. 1 divided by 1 over 16 is 16. So we're multiplying by 16. So you are keeping that constant. That's the thing we want to keep constant. And because we have a random, we picked a random number between 1 and 16. In this case, you picked, the random number was higher than the examples I showed before, section 15. And it just so happened that the 10th section, it does not exist. And that is okay. Because we have a random start, there's going to be some jitter. Maybe 9, maybe 10, maybe 11. The point is we're keeping the section interval constant. So you're good.
Okay, that makes sense now. Thanks for explaining that in more detail. So here's some images of my sections that I'm going to be sampling on based on that section subfraction and the starting interval that Stereo Investigator generated. You can see section 15, 31, and 47 on the screen here, and I went ahead and I manually outlined my region of interest within Stereo Investigator using its contouring feature.
All right, perfect. So we've got our first parameter. We've got our section subfraction. And so now we're going to move on to the area subfraction. And that's made up of 2 things. That's going to be our counting frame dimensions and the grid spacing. So let's get into that conversation.
Okay, so in order to set up the area subfraction, we want to pick a representative section out of our 9 or 10 or 11 sections. So we wouldn't pick the section that's all the way on the right. Notice how small the cross-sectional area of that section is. What we don't want the biggest section, we don't want the smallest section, we want a medium-sized section. So the one on the left would be good. And then we take that section and we can use Stereo Investigator to help us set up the area subfraction.
Yeah, Stereo Investigator makes that part really easy, actually. So I think I got this one covered, Dan. All I have to do is enter the approximate number of sites that I want to have appear or use on my representative section. And in this case, we wanted 10 sites across my section on average for this pilot study. So I entered 10 sites and asked it to estimate my grid size.
And there is the grid size up there, right? 180 by 167.
Yep, and so you can see that's what it has selected to give us 10 sites on this representative section. And now you can see that displayed, overlaid those sites on my region.
So that's what's remaining constant. With the sections, it was every 16th. For this area subfraction, what remains constant, and this is shown by the white dotted line, 180 microns and 167 microns. That's the step among the counting frames. But just like with the sections, we want to give every point on this cross-sectional area an equal chance of being sampled. So it's a random throw. So this is one example of a random throw. And how many do we end up with here? 9, I think.
Mm-hmm. Yeah, 9.
Let's see what the random throw might look like for another animal.
Okay. I'll throw that down again.
Okay, so in this case, notice that the counting frames have shifted and there's a different number of counting frames. Let's see what another random throw might look like.
Yeah, there's 10 here, so we'll throw it again, and if I'm counting correctly, I think there's 11 now.
So don't worry if the number of counting frames is different. That's going to happen because you have a random throw. Thing that we're keeping constant so that it will work in the formula is the ratio of the area of the counting frame to the area of the grid step. So this is not your data, but I'm using it as an example. That's a 30 micron thick section, and that's what the counting frame looks like. That's what the dissector looks like. In 3 dimensions, we call it the dissector. It has 2 red planes and 2 green planes. Of course, you don't see it like that. You see it like this through the microscope with an oil lens. You're focusing up and down, and you're deciding whether the top of the cell is in the dissector or not. So I just show an example of that here. And this is good to review our dissector counting rules. The top of the cell has to be in the dissector. So there is the bottom of the cell, and then we'll move up to the middle, and so that's the top of the cell. But the main reason I'm showing this movie now is for sizing the XY dimensions of the dissector. We want to size it so that we're going to get about 0 to 5 cell tops.
Okay. Let's take a look at my data then. I was able to land on a 30 micron by 30 micron counting frame for my tissue, and I found these dimensions would work well when I sampled my representative section. I moved the counting frame around on that section and usually found that 0 to 5 cells fell within the counting bounds, cell tops fell within the counting bounds. And we can take a look at one of these sites to show you an example of that, Dan.
Yeah, I see you have the Z meter on the right, so that's showing where you're focusing.
And as a counting rule suggests, I'm only going to count the cell tops that fall within the dissector bounds or intersect with the green line, like the cell I just counted there. And over here, I'm going to count this cell because the cell top did not intersect with the red line, even though further down here it does touch the middle, or the middle of the cell does touch the red line.
Okay,
And
I'm glad to see that you're following your dissector rules correctly.
yeah, and you can see that I end up with the 2 cells in this counting frame here. So that's how I went about choosing my counting frame dimensions.
In order to get about 0 to 5 cell tops.
Yeah.
Okay, good.
All right, perfect. So we figured out our section subtraction and our area subtraction. The last of those 3 that we need to figure out is the height subtraction. So let's dig into that.
Okay, so for height subtraction, we can see from this formula that is the dissector height divided by the average mounted section thickness. We could make the dissector the same height as the section thickness. What we're going to do for the section thickness is the program is going to set it up so that we can measure the section thickness at every counting site if we want to, depending on the variance of the section thickness. That section thickness will restrict how tall the dissector can be. And the other thing that will restrict that is that the fact that there is probably artifact on the top and the bottom of your section. So we need something called guard zones. And these guard zones have to be big enough to cover up the artifact. This illustration is representing the artifact as lost cells. That's a little half dotted line there of a half circle. There was a cell in the top and there was a cell in the bottom, but the knife, the action of the knife made that cell pop out. So these guard zones are to protect us or guard against counting where the knife has created artifact. We're counting the top of the cells, so the top guard zone serves another purpose. If we look at that blue cell on the left that's just sticking up at, not that one, but a little more to the left, the blue cell, one more, that one. Notice how that is actually cut off, and we would not count that because its top is not in the guard zone. Sorry, the top is not in the dissector. It's actually in the guard zone. So if you don't have that guard zone there to focus up into to see that cell top, it can be difficult to know whether those cells are cut off at the top or whether the top is actually in the dissector. So the guard zones protect us from artifact, and they make it easier to tell if the top of the cell is in the dissector when you're at the top of the section. So if we put some numbers on this, if we had a 30 micron thick section and we needed to use 5 micron guard zones on the top and bottom, that would mean we can only have a 20 micron tall dissector.
Okay, yeah, so you have to kind of account for the dissector. You have to account for the guard zone height needed when you're choosing that dissector based on the total extent of the tissue that you have available. When I measured my representative section, the mean measured mounted thickness averaged around 20 microns. Even though my tissue was cut at 30 microns thick, it ended up shrinking a bit during the tissue processing step. So yeah, to ensure that my dissector will fit within the Z extent of my sections, I chose to use a dissector of 20 microns. Dan, what do you think I should use for guard zones for this pilot study?
Well, one way to do a pilot study is to actually use no guard zones, because then you'll be counting all the way through this 20 microns, and then we can look at that data and we can look at the counts at the top and the counts at the bottom and see if they're different from the counts in the middle. So by counting with no dissector, we can then examine those counts, and that will help us know how big to actually make the dissector. So I would say let's do the pilot study with no guard zones.
Okay, yeah, let's give that a try and see how my data turns out, and I'll go ahead and get started on counting then.
Okay, so we're going to pause quickly for some questions, and before, as folks are sending those in, I'll just kind of summarize what we've done here so far. We've set the section subfraction to a point that gives us 10 sections. We set our area subfraction that gives us about 10 dissectors. Obviously, that can vary from section to section. And then we set up our dissector that gives a manageable amount of cell tops. Like Aidan said, she found a dimension that gives her about 0 to 5 cell tops. All right, so let's take a question.
Okay, so we've got a question from Victor. He says, there are instances in which counting frames are skipped. Are these skipped counting frames are still considered counting sites and still plug into the formula?
I can take a shot at answering that. Thanks for the questions. So when you say skipped counting sites, I think you might be talking about sites that have 0 cell tops in them. And that is fine, because if you remember, the formula is N equals Q minus times 1 over the volume fraction. So the estimate equals the raw data that you count. We take that raw data and multiply it by the reciprocal of the volume fraction to extrapolate out the raw data to account for places where we did not count. So it's N is proportional to Q minus. And if we add 0 to that Q minus, it does not affect the estimate. And this is true too. Like, let's say you have a ventricle in the middle of your region. It's okay to make the counting frames go over that ventricle, and you'll be adding 0, and that will not affect your count. Of course, if that ventricle is very large, it will affect your efficiency. And so we can do things like exclude nested contours. So if you're talking about counting dissectors where there's 0 cells, that's okay. Of course, they can't all be 0. We want like a mean of about 2 or 3, like 0 to 5 if possible. Now, if you're talking about the fact that some of these counting frames or dissectors are kind of sticking out of the contour, that is okay too, because the grid step is also sticking out of the contour, and that will come out at the end. Let's see, we have another question. Just to confirm, are you saying it is appropriate to use different parameters for control and experimental groups? Yes, and sometimes it's needed because the experimental protocol has changed the way the cells are distributed. They may become more heterogeneously distributed, and you would need to do more sampling. So yes, that is often the case. Almost always, you don't need to change the parameters within a group.
All right, let's see. We have time for one more. I think we do. So next one here is, if I have no guard zone, won't I be counting cells that are cut off?
That's right. You'll be counting cells that are either cut off. Another type of artifact that can happen is the knife compresses the cells, and the density is artificially high because of the knife. But we're only doing this for the pilot study, so we can look at that data. You're going to see, we're going to look at a Z histogram, for instance. We're going to look at the data. Because of what you say, we are counting the cells that have seen artifacts. So we want to look at the data and know how to cover those cells up. And so when we actually do the experiments and count all the animals in each group, we will be using guard zones to guard against the artifact areas.
I think you kind of hinted at it a little bit, Dan, but I feel like this is a great point to kind of jump off and then into our next section.
Yeah, it's a good segue.
All right, perfect.
We'll go to the next section. Take it away, Dan.
Okay, Aidan, let's see what your data looks like using the parameters that we set up in the first half of the talk.
Okay, that sounds good. I wanted to show you some of my data from two different sections. They're actually pretty significantly different, so they'll be good ones to compare and look at together. I've chosen sections 15 and 79 to show you today. And then just to walk you through what I have on the screen, you can see in the first column here how many sites were sampled throughout the contoured region in each of my sections. Following that, we have the runs column that shows the number of cells that were marked within each sampling site. And you can also see those markers represented in the image on the right here. And the last column shows the empirically measured tissue thickness for each sampling site. So in section 15, you see that I have 8 sampling sites total, where section 79 had 21 sampling sites. And I know we were aiming for an average of 10 sampling sites per section, but we talked about how it's okay to have some variance based on our size of our contoured region at that section.
Yeah, that's normal. The bigger cross-section, the sections that have a bigger cross-sectional area will have more dissectors.
And then moving on to the cell tops counted at each sampling site. In section 15, I got a range between 0 and 5 cells counted at each site, and that's what we were aiming for when we selected our dissector dimensions for the pilot study, so that looks good. But in section 79, you can see that the cell tops counted at each sampling site ranged between 2 and 10, so that's a little bit more than we were shooting for. And Dan, I really want to take a look at the thickness measurements with you for these two sections. In section 15, the average is pretty close to 20 microns in Z for the total tissue extent at each site. So it seems like that will work well for the 20 micron dissector I used for the pilot study. But notice there are 3 sites that measure 20 microns, under 20 microns though. Is that okay?
Yes, it's okay if there's maybe 3 or 5 sites that are a little bit, that have a section thickness that is a little bit thinner than your dissector. As a rule, we don't want the tissue sticking out of the dissector. We want the dissector to be contained within the section. But when you're setting up a study like this, it's okay to have a few that are slightly under. It's just something that sometimes has to be accepted.
Yeah, and then in section 79, you can see that that section is much thicker than section 15, averaging closer to 27 microns in a total Z extent. So we have a lot more room to work on this section. And based on your answer to my last question, I would guess that I want to keep the total dissector extent at 20 microns because we're limited by the section 15, that thin section, and we don't want to have more than the 3 to 5 sites that are sampled that are thinner than my dissector. Do I have that right?
That's right. If you had a bunch more 18 micron thicknesses and 19s in there, then you would realize, oh, I need to make my dissector 18, not 20. But even if you brought it down to 18, then you would put up with a couple 17s, if you know what I mean.
Yeah, I'll keep that in mind as we look at the Z extent in my other sections and use that information to select our guard zones. But let me show you the results that we achieved using these sampling parameters that we selected earlier for this pilot study. I have selected, to remind you, a 1 in 16 section sampling interval, and that was chosen to count 10 sections throughout my region. I chose a 30 by 30 micron counting frame in the XY area and a 20 micron dissector height, and I did not apply any guard zones for this pilot study to count between 0 and 5 cells per sampling site. And then I use a grid spacing of 180 by 167 microns, selected when I asked Stereo Investigator what to place, or Stereo Investigator to place about 10 sites across my region on my represented section. And as you've been teaching me, Dan, all of these parameters plus my Q minus, or the total cell tops counted throughout this animal, are going into our equation to estimate our cell population.
Okay. So before we look at your results, let's talk about what we're going to try to do in this part of the talk. Number one, well, you sampled without guard zones. So we're going to use a couple tools. One is called a Z histogram, and one is a process called resample dissector. We're going to use those tools to look at that data that you have collected without guard zones. We're going to look at that to try to figure out how big to make those guard zones. Once we figure that out, we're going to look at a couple other tools. One's called a coefficient of error. You'll see that as CE, and the other is a process called oversampling and resampling. And we're going to ask the question, an important question, have we done enough sampling, and even are we able to do less sampling? So let's recap why we use guard zones. The guard zone is to protect from artifact. In this illustration, the artifact is lost caps, lost cells, and so we need to make the guard zone big enough to fit over any artifact. Okay, so again, this is not your data. I'm just using it to illustrate one type of artifact that can be created from the action of the knife cutting the sections. So on the x-axis, we have the distance from the top of the section. That's why it's called a Z histogram. It has different Z levels on the x-axis. And on the y-axis, this is the number of cell tops that are counted. And we can tell there's something strange going on the top and the bottom of the section. And it's happening for a pretty long, 7 microns on each side. That really cuts into our available tissue to make it so we can only have a dissector in the middle of 9 microns. So that's one type of artifact that we can see.
Okay, well, I think I could. use the Z histogram results that Stereo Investigator exports to create a graph similar to this one. Let's take a look. Yeah. Here's my Z histogram data, and I plotted on the x-axis, like you did, the distance from the top of the section in 1 micron bins, and in the y-axis, the number of cell tops. And this is just for my control animal to remind you. But you can see that I have a really big spike in the number of cells counted in my first bin here.
Yeah, it seems like a different type of artifact.
Yeah, and then the number starts to decrease in the next couple of bins, but I would say it really levels out at around, after around 3 bins or 3 microns from the top of the section. And so looking at this, I was thinking of using a 3 micron guard zone for my stereology study, and here's that dissector that I would actually be counting at.
Unlike the example I showed where that person was losing cells at the tops and bottoms of their section, it looks like you have more cells than there should be at the top of your section. So that could be because the knife has compressed the tissue up there. And it also has to do with this idea that it's easier to tell if the top of a cell is cut off or in the dissector if you have a guard zone on the top, so that you can focus up and actually see the cell top in that guard zone. So I think that's a good choice, this 3 microns on the top and the bottom. And that was called Z histogram. This is another process that we can use to help us pick a good guard zone. And this is called resample dissector. So on the left, these are the 9 sections that we've been using. And on this graph, on the x-axis, it's showing the size of the guard zone. So if you look at 0 on the x-axis, that's the data with no guard zones, and the estimate, so that data gets put into the formula. This is a 4.5 times 10 to the 5th is that estimate. And then our program will add guard zones. So if we look at 1 on the x-axis, that means now there is a guard zone of 1 micron on the top and the bottom. So what we're doing is we're covering up that, artifact that we saw in the last graph where there's more cells than there should be. And because we're covering up an artifact whose nature is too many cells, we get a estimate that is less. So this is making sense along with the Z histogram, and it's kind of verifying that the 3 micron guard zone that you picked from the Z histogram is appropriate. We really want to cover up that first micron, and let's go ahead and cover up 3 microns. So I think that's a good decision, based both on the Z histogram and on this resample dissector.
Okay, so in that case, I have determined using my empirical thickness measurements that I have 20 microns to work with from the top of my tissue to the bottom of my tissue. And if we were going to introduce 3 micron guard zones on the top and the bottom of my sampling sites, that would remove 6 microns to work with in my dissector. So 20 minus 6 leaves me with 14 microns for a dissector height if I wanted to add guard zones for the rest of my study.
Yeah, so it can really be a challenge to get a tall enough dissector to count in between getting thick enough sections to start off with, and then we have this added thing of adding the guard zones in, and that will cut into your dissector. So we're ending up with this 14 micron dissector, but that still should be enough to focus up and down and find cell tops. Okay, so we said we wanted to choose the dissector size, and we've done that, 3 microns. The other thing we want to do is ask the question, have we done enough sampling, and could we actually maybe do less sampling? And this first tool that we're going to look at is called a coefficient of error, or a CE. Can you tell us a little bit about this data, Aidan, from one animal in your control group?
Sure, yeah. So here, Stereo Investigator has provided the population estimate for my control animal calculated based on our sampling parameters that we selected, the empirical thickness measurements that I made as I was counting at each site, and the Q minus, or the total number of cell tops counted. And you can see that I've obtained a Q minus value of 680 with our pilot study design. We were expecting closer to 250 cell tops instead of 680. And we were aiming to count 10 sections and 10 sampling sites per section and an average of 2.5 cells per dissector to get that 250 cell tops. So looking at the Q minus for my data, you might say that I oversampled and have a little bit of room to improve on efficiency here. And I also put my Gunderson CEs for this animal up on the screen. I have a M0 Gunderson of 0.06 and an M1 of 0.04. Dan, do you think that those CE values also suggest that I could get away with a little bit less sampling?
Yes, they're under 0.1, so they do indicate that. So let's take a look at data from 2 animals, one from each group. The Q minus, that is again the raw data. That's the cell tops that you count in all the dissectors and all the sections that you're using. For the control animal, as Aidan said, is 680. And she also counted a treatment animal, and that came out to, using the same parameters, that came out to be 592. We want to do a pilot study on one animal for each group because there could be differences in how the cells are distributed between groups, calling for different parameters. So when we take that Q minus number of cell tops and put it in the formula on the right, which has to do with the height subfraction, area subfraction, and section subfraction that we've been talking about, we get an estimated number of cells of 4.54 times 10 to the 5th for control, and for the treatment, 2.99 times 10 to the 5th. So it looks like at least the means are bearing out your idea that these groups are different. So what is this coefficient of error? It is a formula that helps us think about the precision. That means the number of sections and number of dissectors that we use. These formulas are set up to gauge the variance of your counts between sections. Some of them do that. Some of them gauge the variance of the counts between dissectors. And because, now this is showing the result of one of several CE formulas that are available in the program. We are not looking at the formulas of the CEs today. We could probably do a whole webinar just on that, but there is a link there to see the formulas and the references. Because the CE is below 1, that indicates that we could possibly get away with more counting. At this time, I want to take a little tangent and talk about another use of the CE, which is it's very useful after you've done all the counting of the subjects, because what the CE tries to do is estimate the CV of the variance that is due to sampling. Not the variance that's due to biology, but the variance that's due to sampling. So you can use it to estimate the amount of the variance in your results that's due to sampling. And there is a reference at the bottom, especially look at Part 8, Good Enough Estimate Precision, to learn about this. But back to the pilot study, we look at the CE. If it's below 0.1, that indicates maybe we can do less counting. And we have a tool in the program called Oversampling and Resampling that can help us kind of figure out how much less counting to do. Okay, so again, this is not your data. This is data from someone else that I'm going to use to illustrate how we can use this tool Just like your data, there's two groups, and the mean of one group is different than the mean of the other group. If we look at the high mean group, which is the blue dot, and we look at 1 on the x-axis, so on the x-axis, that's the sampling interval. So that is the oversampled animal, and it's giving the population estimates on the y-axis. So we have all this data, and our Stereo Investigator can ask the question, what if you had looked at every other site or every other section? So for that, we look at 2 on the x-axis, and the program looks at every other site. So it looks at just the odd sites that you're using, and it needs to extrapolate that out twice as much. And then it looks at the even sites. This could be sites or sections, and it gives you 2 estimates for that downsampled data. So in other words, if we did half the work, we used half the number of sites, that shows the 2 estimates we would get from the data. And that might be okay to be there, because what we can do is examine these 2 graphs as cones, and then find the spot, find kind of the sweet spot here, which is represented by this green dotted line. And we want to be to the left of this green dotted line. So let's say we were at 5 on the x-axis. That means we are reducing our sampling by a factor of 5, either for sections or for sites. We'll give you 2 graphs. And that would probably be okay, because a high estimate from the low mean group will not overlap with a low estimate from the high mean group. Yeah, so that one there is a high estimate from the low mean group, that orange one right there. And notice that's pretty far away from a low estimate from the high mean group. So that's why we want to be to the left of that sweet spot. So I think this would be a good thing to do with your data.
Okay, yeah. So here is the Excel exported data from Stereo Investigator for my control animals, oversample, resample, and I have shown the Excel file for the site interval and the section interval. The site interval is up here on the top, and then down here is my section interval data. How do I get this information into a graph that's similar to yours, Dan?
Yeah, let's first notice that we're showing the 9 sections that are being used on the top. And if we look at the site interval graph and we look at 1, that is the oversampled situation. So this is the estimate that we're getting. That's that 4.5 times 10 to the 5th. And then on the number 2 column, the program has looked at every other site. On the number 3 column, the program has looked at every 3rd site and extrapolated it out appropriately. If we look at the number 19 column, it's looking at every 19th site and extrapolating it out. And if we look at the bottom, that is done for sections instead of sites. So for number 1, that's an estimate with all the sections. If we used every other section and extrapolated each one of those out twice as much, now we're getting 5.1 times 10 to the 5th and 3.9 times 10 to the 5th. Instead of reading these off the chart, let's graph them.
Yeah, I think now that you explain that in more detail, I can organize, and I know how the charts are organized here. I can figure out how to create a graph that was similar to your example. So here's what I put together, and you can see I made graphs for both the oversample, resample results for the site intervals and the section intervals. I have also done this for both my control animal shown in yellow and my treatment animal shown in green. And let's look at the site interval graph first. You can see that I have put the cones on, and the overlap of those cones between our treatment and control groups is a site interval of about 8, somewhere around there. But look at site 5, a site interval of 5 here, Dan. These estimates are really close together. close to overlapping, would you feel comfortable decreasing your sampling sites by a factor of 5 after looking at this data?
That is what you have to decide. These tools give you this data, and then you look at the data and you do what you feel comfortable with.
Okay. Yeah, I think that I might stick with reducing my sampling site interval by a factor of 2 instead. Here, I'll put that up on the screen.
I don't
I
think
wanted to play it safe because I know that with the resample dissector, we saw that my new guard zone implementation of a 3 micron guard zone on the top and the bottom is already going to decrease my total cell top counts and my Q minus. So I think that I want to play it pretty safe.
Yeah, I don't think that is dangerous at all to use half the sites because the high estimate for the low mean is pretty far away from the low estimate for the high mean. And that's a good point that you made, that we have to keep in mind that our guard zones are going to cover up cells, so that's going to reduce our raw data. So that's another reason to be kind of careful about not going to number 3 or number 4 or reducing by a factor of 5. So I like that decision.
Okay, and then looking at the section interval oversample resample data, I see that my estimates have a wide variance even with decreasing the sampling interval by half here.
The sections, yes. You'd be going down from like a mean of 10 to a mean of 5. Yeah, you'd be going down. You picked that section interval, which was 16, and that gave you 10 sections. So when we go to 2 on this graph, that means we're using about 5 sections instead.
Yeah, since I might see more variance on other animals in the study, I really wouldn't feel comfortable decreasing my section interval by a factor of 2. So I think I'll stick to the current section interval that I have chosen.
Yeah, 154 sections total, and using just 5 sections, I think would make a lot of people nervous. And looking at that graph, comparing the low mean from the low estimate from the high mean group and the high estimate from the low mean group, I agree not to slide over to every other section, but keep it with about 10 sections.
Okay.
Okay. So I think we have hit our goals. We used a Z histogram and resample dissector to demonstrate that your guard zone should be about 3 microns. By the way, that animal that ended up being oversampled, the one with the 680 cells counted or so, you don't have to redo that animal because you've overcounted. That just means you've been more thorough than maybe you needed to on that animal. But you can use the resample dissector data at a level of 3 micron guard zone and include that as one of your 5 animals or however many you're using per group. We also asked the question, have we done enough sampling and can we do less? Our CEs were below 0.1, and so we used oversample and resample, and you made the decision to cut your sampling sites in half. So now you go ahead and you count all the animals for every group. As you count the second animal, go ahead and check its CE and see if we're on the right track here. If you come out with a significant difference at the end, well, that means we did this pilot study right and we picked the correct factors. If you don't have a significant difference, well, that's why we've kind of gone to the trouble of setting up this pilot study, because if a colleague or a reviewer asks you, do you think you would have had a significant difference if you had done more sampling, you would say, no, I'm not going to do more sampling because look at my pilot study.
Yeah. I am feeling so much more confident now, Dan. Thanks so much for going through my data with me. I am going to keep counting the rest of my animals. I'm ready to finish my optical fractionator experiment.
Well, that's all, folks. Thank you, Aidan and Dan, for walking us through this comprehensive example of a pilot study. Here you can see some of the resources that Dan and Aidan used to put this presentation together.
Those are mostly for the CEs and things like that. These are some reviews we recommend that will go through the things that we did today about a pilot study, and also a lot of other information about unbiased stereology.
Okay, and before we take questions, I just wanted to touch on a few resources and ways to get a hold of us. If you want to learn more about Stereo Investigator, please visit our website. We also have stereology.info, which is an amazing resource that goes very in-depth. Dan is one of the main curators on that site, and we go in-depth on not just the optical fractionator, but many of the probes, all the probes that we do offer in Stereo Investigator. You can also reach out to us and talk to a stereology expert on our support team. We've got PhD neuroscientists like Dan. We've got folks that have walked through and done these experiments, so we're happy and we're here to help if you have questions or run into trouble. You can post a question on our forum. There are many questions posted there already, or if you don't see yours already asked, then you're welcome to post there as well. We also have our YouTube channel, like I mentioned earlier, with other webinars. We also have started office hours. So those are once a month. Those are going to be, for the most part, the second Friday of the month. We may have to shift here and there, but that's kind of what we're going for. And we'll be discussing different topics from the MBF offerings. And we almost every month will have a stereology session going in there. So please join us for that. We're excited and happy to talk to folks with questions and want to keep you all moving forward. And then we do have a survey after this. So after the webinar finishes up, please take some time to fill that out. We'd love here. Again, we really want to get the feedback, what you like, what you didn't like, if you have further questions. And thank you so much for taking time out of your day. We know how busy everybody is. So thanks for joining us. We really do. This is a really good opportunity for us, and we're really excited to have you here with us. So thank you again. And then we do have upcoming webinars. We're trying to do at least once a month. So please check in on those. These aren't all scheduled yet, but we will be doing these webinars this year. So we've got quite a few coming up, and we're really excited about those. So keep your eye out for those. We'll have those posted on our social media, and we'll be sending out emails about those. So if anything looks interesting, feel free to write in, and we'll get you on the list to get those emails. And I think we're ready to take questions. So feel free to send those in.
Okay. Well, let's see. We've got our first question in here. It's from Gavin. How many microns is generally acceptable for the interval between Z-stacks?
Well, you need an interval that will let you section through the cell several times, many times. What we want to do is, well, let's see. Okay, interval between Z stacks. Oh, okay. I think I missed.
Is that the SSF then?
Yeah, I was
Okay.
answering. I was I was addressing the within a stack,
Right,
which might be like 1 micron interval. But I think this question is asking more to do with, like you say, the section subfraction. So you want to set up an interval that will, for the pilot study anyway, that will give you a mean of 10 sections. So if you had 120 sections in total, you'd use an interval of 12.
makes sense.
And so the question is asked, how many microns is acceptable for the interval? But when I think of an interval, I think of sections. When I think of the section subfraction, and each one of those sections would be made up of a certain thickness. That actually leads into the next question, I think, Nate.
Yeah, so we've got a question about what if, so I was just asking about sectioning the tissue and how thick that should be. So the question is, I may have missed this, but does tissue fixation and sectioning thickness affect the pilot study? In other words, what if we sectioned at 35 or 40 microns? So it's a really good question. We get questions like that very often. I'm going to take a stab at it here and jump in if I leave any holes. But the section cut thickness is a critical piece for us to know. But even more important is how thick that tissue is when it's mounted on the slide. And that will help you determine how much space you have to work with as you count. And so as Dan and Aidan were talking earlier, and they were talking about that guard zone, you want to have some room in your section thickness for that guard zone. And as you saw in Aidan's data, those first couple sections, there was huge, skewing of the data. The first couple sections, there was a bunch of extra cells. You could see in that example how of the cross section that they had, how that could happen, where you're counting maybe not the top of the cell, but kind of after that top has started. So
it might be good to mention, Nate.
Yeah.
Specifically that Aidan cut at 30. Correct me if I'm wrong, Aidan, and they shrunk down to 20.
Yeah. Yeah, I was just going to mention the same thing, that tissue fixation can affect your measured mounted thickness. So if you're changing your fixation protocol between groups or even between animals, that is going to affect potentially how much you have to work with in Z for your section thickness when you measure that empirically after the fixation process, because shrinkage may occur.
Should we get into why that shrinkage occurs, Nate? It's osmosis. When you're doing your histology, you bring it through ascending alcohol steps at the end, 70%, 80, 95%, 98% alcohol. And that sucks a lot of water out of there and will cause it to shrink. That's why Aidan's went from 30 to 20.
And that's not, like, it's very common. This happens. This is a thing that happens if you get to a threshold where you're really not sure if you can fit guard zones and some room for a nice healthy dissector, let us know, and we can help you through that, how to work through that. If it's trimming the guard zone, maybe asymmetrical guard zones, maybe a different probe entirely, but we can talk about that.
There's ways to do histology without ascending alcohols and things like that. Yeah.
Yep. So depending on where you are in your process.
But yeah, they say, what if they sectioned at 35 or 40? Then probably they would have a thicker section after the artifact, but we found it's not really a linear relationship, and you have to do it empirically. And don't forget, the thicker you get your sections, the harder it is going to be for your antibodies or whatever you're visualizing with to get into the sections.
Yeah, it's definitely a balancing act to find that happy medium. All right, what do we have? Next question. Let me see. Are there rules between physical and optical dissector? No.
I think it's saying, like, can you use the same guidelines for a pilot study for physical fractionator and other probes, maybe? Right.
So the probes themselves would have different rules, but the pilot study would be the same idea. Shoot for 200 to 300 and take a look at your CE.
Perfect.
Let us know if we answered that question fully.
We've got a follow-up on the previous one. What is a healthy dissector thickness? Do we have any guidelines on what's a good amount for a dissector thickness?
It depends on what you're counting. But if you're counting kind of a typical cell from the brain that's 25 or 30 microns in diameter or something, something like 20 micron dissector height, and we found with our customers is plenty to be able to focus up and down with an oil lens. You're using an oil lens, so it'll give you a resolution of like a micron or less even. 20 micron dissector with a typical cell, it's probably going to be good.
Yeah, I think that the dissector thickness is also something that comes into play as you're trying to get 0 to 5 cells within your counting frame or your optical dissector. So if you are counting, or if you have your counting frame dimensions pretty small already and you're still getting more than 5 cells per site, you might consider decreasing your dissector thickness to reduce the total number of cells that you're counting in that site, in that sampling frame.
But that's not a, that, if people are facing that, they're in good shape because their tissue is pretty thick, right?
Yeah.
Okay, let's see. We've got some more questions. What do we have?
Dissector is spelled with one S, by the way. They're trying to coin a new word.
Okay, so next question we have is, how would you choose the size of the counting frame and grid spacing for the dots and sampling interval with the area fraction fractionator probe? So there's a different probe, but
yeah,
another question about setting that up.
So you remember at the beginning of the talk, we talked about how you can estimate number, but also length or surface or volume. So this comes under volume, and area fraction fractionator probe is a probe to estimate the percent by volume of one type of tissue, one phase of tissue. People use this for instance, plaque load in the cortex a lot. What's the percent by volume of the plaque? So for the section subfraction, it's the same thing. Let's try to get an interval that gives us about 10. For the area subfraction, that's the same thing. Per section, let's look for about 10 counting frames where we're going to have points. These points are going to be put down on the counting frame, and our job is to put one kind of marker, say, on the plaque, and another kind of marker on non-plaque region. And so, let's see. I am showing stereology.info right now, and we can take a look at this top chart. Let's go up a little bit. Let's see, can I control that? Yes. Okay, so this shows all the probes. Here's volume, capillary point counting. Here's surface. It's a probe called the isotropic Fokker. Here is length, that's Spaceballs, and here is optical fractionator for that we just went through. So we want to be looking at volume or capillary point counting. So this shows capillary point counting. Let's take a look at over here. What are you estimating? And again, we break it up into number, length, surface, and volume. So I'm going to go to volume. And this shows right down here, area fraction fractionator. You can use thin sections. You can orient the tissue any way you want. So you're asking about a pilot study for area fraction fractionator. And like I said, for sections, it's the same. Let's shoot for 10 sections. Let's shoot for an interval between these counting frames where the points are of about 10 counting frames. Up here we have probe index. You can look at the probes in action. Let's go to the area fraction fractionator. So this would be one counting site. Remember, we're shooting for about 10 per section, about 10 sections. But now this gets a little bit different than the optical fractionator. The optical fractionator is a 3D volume where we're focusing up and down, finding the tops of cells. This is a 2D counting frame. And our job here is to put one type of marker, in this case over plaque, a yellow X, and another type of marker where there's no plaque. And it takes the number of markers on plaque and divides by the total number of markers. That gives you an estimate of percent by volume. So how do you set up the pilot study? One thing you have to think about is the distance between these points. And so you set the distance between the points so that you wouldn't miss what you're looking for. That's why I set them close enough together to catch this plaque. We would, and so you do a pilot study and look for maybe a couple hundred of these yellow X's, and then take a look at the percent by volume. And we actually give you a CE for this. In fact, the CE was invented for volume before it started being used for number, at least the Gunderson CE. And If you are seeing the same number of yellow X's from section to section, that means you've got a pretty homogeneous situation and you might be doing enough counting. But if you're getting variance in the number of yellow X's from section to section, that means there's variance in the amount of plaque or whatever you're trying to estimate the percent by volume. And that would indicate to increase your sampling by increasing the section subfraction. You may need to put these plus signs closer together if you're missing the plaque. So that's the type of thing to think about when you're doing a pilot study for a probe that does point counting.
Awesome. Thank you. All right, we have next question here. We're looking to count with our 20x objective with the optical fractionator. I've noticed a lot of the literature, it says we should use 100x. Is that really necessary? So the magnification is important, but the most important piece here is the NA, so the numerical aperture value of your objective. And that will give you that thin depth of field to be able to discern when does that cell top come into focus. And one of the big sayings that we have a lot with stereology is you want to give the object, the cell in this case, the chance to be counted once and only once. And the best way to do that is get that really thin depth of field that you'll get with an oil objective. So maybe not necessarily the 100x, but we do recommend an oil objective typically that's going to give you that thin depth of field with an NA of over 1. Dan, anything you wanted to add to that, or?
Yeah, you can answer that question for yourself empirically by trying the 20 times objective. And I think you're going to find that you do not have many planes through your cell, and therefore you can't optically shave off a top of the cell. And I actually read a lot of the optical fractionator papers that come out, and the biggest mistake people are making is counting at low power. They're not sure whether that little black dot they see is a whole cell or a half of one or a third of one. And so by figuring out empirically, what I mean is put it up on the microscope and focus through the cell and make sure you have many focal planes through the cell, and you can actually focus on just the cell top. You know, if you're counting something that's punctate and you've collected it with a confocal, then you're going to be able to get away with smaller dissectors. So really, you can figure this out empirically. But what we know is that you're going to find out that you almost always need to use an oil lens to have good enough resolution in Z to have nice thin Z planes to optically be able to shave off the top of that cell.
Perfect. All right, so our next question, so it addresses bringing images in from a confocal. So instead of acquiring the full region of interest in the stack from the confocal, is it possible to acquire stacks at each sampling site and count in Stereo Investigator Optical Fractionator?
Yeah, that's what we just showed. And many confocals and more lately are allowing you to collect in a grid of a known dimension. So if you do the systematic random sampling and you know the X and the Y dimension between your stacks, we have a feature in the program where you can load those in and enter that information. We call it the grid step. It's the area among counting frames. And so, another way you could do this, if you have the resources, is to do a 3D scan slide and open it in our program, and then you can just work on that. Of course, that's much more resource intensive than actually collecting only the stacks you're going to use. You can do it either way in our program.
Perfect. So yeah, the short answer that's definitely yes. And we've got some features that have been optimized for that, because that's a really common request these days. And it frees up the microscope and allows you to kind of work wherever you install Stereo Investigator.
We're really glad to see that happening too.
Yeah. Okay, the next question is, if there's a missing section during the study and there's no substitute for the missing section, what should be done to ensure that the results are not affected?
Okay, a couple different ways to deal with a missing section. You know, you're doing every 16th section and you don't have one of the sections. Well, one thing you can do is just go to a next door section. If it's calling for section 15 and that's been ripped or lost or something, you could use 14 or 16. It's okay to have a little jitter in your section subtraction. Another thing that you could do is take the mean of all the other sections and stick that in for the missing section. That would be if there isn't one next door to use, because that's a little bit that's worse than using a neighboring section. What we're trying to do here is avoid humanely killing another animal. So if there's one section missing, you could use one of those methods. Either look at the means of the surrounding sections and just put it in there, or use a neighboring section. Definitely don't do it with more than one section. But those, and that would be up to you whether you wanted to slightly compromise your data like that. And of course, you'd want to report it.
Perfect. All right. We did have some questions about stereology and machine learning. AI is obviously a buzz topic. Machine learning goes hand in hand with that. So we do have a product that is coming to market soon. It's currently in beta. So that's in the works. And Aidan, did you have some more information about that?
Yes, so far we have algorithms trained to automatically quantify cells within while still adhering to the stereology rules for a few different labels, including DAPI, NUN, and IBA1. And so if anybody has any data that they'd like us to try out with these specific algorithms, see if the product works well with their data, we would be glad to help out with that. And if you'd like more information just in general on what Solaris is designed to do, there's a survey after the webinar, so please let us know in that and we can be sure to follow up with you.
Awesome. Okay, so I think that's about it for today. If we didn't get to your questions, we apologize. We'll try to reach out to you if we have those. But thank you everybody for sticking it out with us. I know an hour and a half is a long time, but there's a lot to cover, and we wanted to share all that with you. Again, we will have the office hours. We don't have the date set on that yet, so just be on the lookout for that. If you have more questions, we're happy to chat with you about that. Dan, Aidan, anything you wanted to add before we head out?
Just thank you all
Thanks,
for your
everyone.
wonderful questions. Yeah.
All right,
Thanks
everybody.
for joining.
Take care.